निलेश सर हे करा. हॅलो निलेश सर. दिनेश सर गुड मॉर्निंग. लक्ष्मण सर, राजेश सर.
Lakshman, good morning.
Good morning. Bhagwat sir, good morning.
Good morning, everybody. Good morning, everybody.
Good morning.
Good morning, sir.
Good morning.
Good morning, everybody.
सुदेश सर, मी तुम्हाला हे co-host बनवलेलं आहे. दिनेश सर.
Yeah, Milan. Yeah,
You
Milan.
are also co-host.
Okay, Milan.
सुदेश सर शेअर करून ठेवताय का हे?
Can you see it, man?
Yes, yes. Yes, sir.
Good morning, Bhagwat sir.
Good morning.
I'm Namrata Ajwani from Physics Department.
सुदेश सर आमचे HOD आहेत मॅडम.
Good morning, madam.
आणि दिनेश सर व्हाईस प्रिन्सिपल आहेत. IQSC कोऑर्डिनेटर आहेत. शाश्वती मॅडम फ्रॉम केमिस्ट्री डिपार्टमेंट, राजेश सर फ्रॉम मैथमेटिक्स डिपार्टमेंट.
Morning, sir. Thank you for accepting our invite for this very important workshop.
Yeah, I was more than happy to do it because unfortunately, had it been a physical one, I would have been more happy.
Yes, sir. Yeah.
Cannot complain.
Very true, sir. Very true. For this very important workshop.
आणि निलेश पाटील सर आहेत केमिस्ट्री डिपार्टमेंटचे.
Okay. And I'm more than happy to share
Zora
whatever
ma'am from
information I
chemistry.
have.
Milan, kindly check the number of participants that have joined overall, including the YouTube link. And when you're good to go to, then
Yes,
we can start the
YouTube
program.
94 and
Okay. Okay.
and Zoom there are
9.
9.
Yeah. So just we can wait for some more time, and once Dr. Kiran ma'am joins, then we can take this forward with him.
Yes, sure. Good morning, Kiran ma'am.
Good morning. Good morning.
Madam.
Kiran,
Yeah.
Mona is yet to join.
Okay. I just call her.
Yeah,
Rajesh
do
sir,
that,
good
na?
morning. मॅडम तुम्हाला मी कोविड बनवलंय किरण मॅम.
Okay. Okay. ठीक है. I'll just call Mona and then we can.
Oh yes, sure.
Mona is joining. Milind, how many students have joined as of?
एक मिनिट हा. 180 युट्यूबला आहेत आणि इथे आपण सर्व फॅकल्टीज आहोत.
Okay. Okay. ठीक है. Welcome, Sudesh.
Thank you, Kiran.
So we're all set. We just wait for another 2 minutes. Students are still joining. So. Milind, just let me know when to start. We'll start in another 5 minutes. It's 10.
Yes, sure ma'am.
We should not make delay it a lot. Okay.
Kiran, I have 2 presentations to make. I don't know whether 3 hours would be enough. So we will take a call on the second presentation.
Okay.
If it is, say, if I complete the presentation by 11:15, then we take the second one.
Okay, fine. No problem. No problem.
I'll probably come back in 2 minutes.
Yeah.
Milind? Milind?
हा मॅम बोला.
Are we sending the Zoom link to students also?
येस द्या. चालेल पाठवा आपल्या
पाठवू?
टीवायच्या मुलांना. येस टीवायच्या मुलांना.
Mona
निलेश
is
सर.
joining, and I suppose Akhilesh Mehta is also joining from the maths department.
Okay.
Okay. Yeah.
I'll put the Zoom link on the groups.
I think Namta 100 people can join on the Zoom. So I think now we are only teachers are there.
Yeah, that's why
13 participants. I think we
I'll
can
put it, na?
Yeah.
हा येस मॅम.
And Milind,
हाँ बोला मैम.
Dr. Sudesh wanted that question and answer sessions अलग से नहीं रखेंगे. If anybody has a question, they can put it in the chat box.
Yes.
So you and Nilesh, both of you
Yes.
have a look at the chat box, and if there is a question, we can tell him, because he says he would like to address the questions at the
Yes.
same
Yes.
time.
Yes. No problem. No problem.
At the end, matlab, it becomes very, I mean,
Yes.
ambiguous
Yes.
ho
Yes.
jata hai.
Correct.
So
Correct.
he wants it on the same time. Okay.
Even YouTube वर पण काही क्वेश्चन असेल, we will take.
So you can just request him, and then he can answer the questions.
Yes.
Okay. Mona, welcome.
Good morning, ma'am. Good morning, everyone.
Good morning, Mona.
Now, Helen, you will mute all the students.
Yes. Yes. Sure. Sure.
You will mute all the students.
Yes.
They cannot assist you, because I don't want this whatever.
Kiran, I think 100 are up in Zoom.
85 participants in the meeting, so 15. I think we can start now.
Manoj sir, good morning. Dear student,
morning.
good morning. Good morning all.
Good
Dear
morning.
student,
Manoj.
Good morning, Manoj.
Good morning, ma'am.
Mona ma'am, good morning.
Good morning,
all.
Good morning, everyone.
Good morning.
Good morning.
Good morning, Shashwati.
Good morning, Kiran ma'am, Mona.
किरण मॅम
morning,
डायरेक्ट किरण
Yeah.
मॅम मुलं डायरेक्ट इंटरॅक्ट करू दे की त्यांना चॅट बॉक्स मध्ये सांगूया?
Chat box.
चॅट बॉक्स.
Yes. Let us not open their, allow them to speak. I don't want that to happen. Okay. If they have questions, let them put it in the chat box. Okay.
Milen, 100 on Zoom, right?
Oh
We are
yes,
done.
yes, yes. Bus, yes, yes.
Let's put a message that join the YouTube.
YouTube. Yeah.
Okay.
And you're recording it, Milind?
रेकॉर्डिंग मॅडम डायरेक्ट युट्यूब वर आहे ना?
Okay. Fine.
Milind, share YouTube link in group also, so DBT group, so that I can share with my student
ठीक
also.
आहे. निलेश सर कराल का? निलेश सर मी करतो.
ओके, करतो सर.
येस. Dear student, if you have any question, you can put in chat box. Kiran ma'am, there are total 100 participants.
Okay. So I think now.
Namrata ma'am, can we start?
Yeah, I think we can start.
Dinesh
Yes,
sir?
we can start.
Yes.
Only YouTube हमें नहीं आता है.
I'll check.
I
152 है.
I think Kiran, we are good to go.
Yeah, we are good to go.
Dear student, if you have any question during session, you can put in chat box.
So we will start now. Is sir back?
I will check. Sudesh sir,
Yeah, Kiran is there. He's there, Kiran.
I'm online.
Okay, okay. So we are starting now. Okay. So good morning, everyone. On behalf of RD National Principal RD National College, I welcome you all to this workshop on solar energy. And I would also like to introduce to you the faculty members of RD National College who are present here. We have with us my co-vice principal, Mr. Dinesh Himmat Singhani. He is also the IQSC coordinator. Ms. Namrata Ajwani, the head of the physics department. Mr. Anand Sethi, the head of chemistry department. We have Dr. Mona Kejriwal, our DBT coordinator, and many faculty members from the physics and the chemistry, Dr. Nilesh Patil, Dr. Shashwati Pradhan, Mr. Manoj Kadam, Dr. Lakshman Jathar, we have Dr. Rajesh Raut. So welcome all of you and all the students from RD National and from other colleges. To start with, I would say that the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved up the face of the waters, and God said, "Let there be light," and there was light. That light, I suppose, is that of the sun, the source of life on earth. Past, we are all worried about what will happen once the fossil fuels are not there, and how are we going to get the light we have today in our life. And that is, I think solar energy is one of the answers to it. It says that the past is gone, it will never lasts, tomorrow is here, showing with blast, taking steady steps, keeping hope alive. That's motto of this workshop, and that is our drive. With this, I would like to introduce to you today's speaker, Dr. Sudesh Bhagwat. Dr. Sudesh Bhagwat is a PhD in physics from the University of Mumbai Institute of Science. He has worked in TIFR. He is a solar PV specialist, expert, DABS, ADB funded projects. He has worked as renewable energy advisor at DABS projects. After he finished his PhD in 1999, he joined Freie University Berlin, where he worked on the cutting edge research of memory devices. He moved to Planck Institute, Halle, Germany, to continue his research on memory devices. In August 2005, he joined Samtel Center to Display Technologies, IIT Kanpur, and was a part of product development unit developing organic light emitting diodes for mobile phone applications. He also worked on organic solar cells during his stay in IIT Kanpur. In 2008, he joined Videocon Industries and worked on solar projects. The list is very long. If I go on reading, I think it will take another half an hour to introduce him. But latest, his research experience, he has got more than 25 years of research experience in solar technology in national and international labs. And lately he has worked with Afghanistan Ministry of Energy and Water, Government of Afghanistan. So now, without taking much of our time, with this brief introduction, I would request Dr. Bhagwat to come on the dais and start his workshop for today.
Thanks, Dr. Kiran, for the introduction. I would like to add a few more points. Basically this talk is more to, incite some kind of excitement in the students to look at solar as a career. So right now I am working on a Asia Development Bank funded project, but I have worked quite a lot with the World Bank, the United Nations Development Program, and USAID, which is the United States Assistance for International Development. And all these works I have been doing it in a very exciting place in the world, in Central Asia, which is Afghanistan. So I have been advising the government of Afghanistan and the only power utility, which is the Afghanistan Besna Sharkat, on renewable energy matters. I have been active in solar for the last 12 years since the inception of the National Solar Mission, which was Indian National Solar Mission, which was announced in sometime in 2009. And me, along with my team, I have built quite a few mega plants, and that is the land-based projects and also rooftop projects. So right now, currently for the last 6 years, my focus has been in Afghanistan. And as a part of my assignment in Afghanistan with all these international multilateral funding agencies, I also do some capacity building for the national Afghan engineers and science graduates, because constructing power plants is one thing, but you need to have trained manpower to also build these kind of infrastructure projects. So that kind of capacity building work also I do with the Kabul Polytechnic University and Kabul University. And I also assist the Afghan, because once the power plants are up and operational, and before they are up and operational, you need to have some standards the way we have in India. So I'm also assisting the Afghan National Standards Agency to set up the standards. And why solar? I mean, Dr. Kiran has already told you why we need solar, because that is the only free and renewable energy source which will be giving power, because fossil fuels sometimes at some point of time will be completely exhausted, and you need to have some kind of renewable energy. So solar is one. You could have also wind. You could have hydro projects as well. So this brief introduction, let me start. I mean, I will take you through a journey of photon from the sun, from the sun to the light bulb which is lit in your house. And you can see this cartoon character is Buzz Lightyear from Toy Story, and his catchphrase is "to infinity and beyond." So let me take you through this journey of to infinity and beyond. I will start with a very small a story which was written by my son when he was young, because he used to see me. He used to see me working in solar and interacting with quite a few engineers. And since he was more of a what do you say, a Toy Story fan, I will start the journey with the story written by my son Rudram Bhagwat. So the story goes on thus: I, a photon, a particle of light, was born millions of miles away from the earth, and I was formed on the sun. As soon as I was born, the sun commanded me to travel to earth. After a quick 8-minute journey, I mean, this is the time which is required by the sun rays to come and hit the earth. I reached earth wondering where I was going to land. To my utter curiosity, I saw a small blue panel, which is the solar panel. I landed on it, and I was sucked within it. I felt myself transforming to something different, and before I knew it, I was sitting on the bulb of a room. So I am going to take you from the sun to the bulb in some room, in some remote place, or in a city, in any place of the world. Once we are talking about solar, let us see what are the examples of solar powered devices? I mean, you know that solar power plants are used to generate power, but there are some other small examples as well. You can see this is a solar powered torch light, which is, the battery is in the torch and it is charged by solar. The solar street light, which you can see here, is a very normal thing and which you see all over India nowadays. This is a solar water heater, which converts solar light into heat. This is a solar cooker here, which you can keep some food articles in this solar cooker and cook the food articles. In the center, you can see a solar concentrator. This is this solar concentrator will convert light, and this is just a parabolic mirror which converts solar into heat, and heat is then transformed into usable energy. And this kind of solar concentrator can be seen, I think, in many of the places. The biggest one being in Shirdi Sai Sansthan, where they have this kind of solar concentrator which they use to generate steam, because they have a lot of steam requirement. The steam can also be converted into run turbines, and you can generate power from there as well. So since we are talking about solar, let us see how does the solar spectrum looks like. So this is the solar spectrum. On the x-axis, you can see there is a wavelength, and on the y-axis is the intensity of light measured in watts per meter squared, and wavelength is measured in microns. You could have it in angstroms as well. You can see that the visible spectrum is only 47% of the light which falls, which is right now usable using the existing solar technology. 2% of it is UV, and more than 51% of the light which is falling on the earth is on the infrared zone. So that way, once the solar sun rays fall on the earth, 50% of more than 50% of the energy you cannot use with the existing technology for solar PV. So only for 47% of the energy is used. So now, in terms of the energy spectrum, what is the whole energy spectrum has an energy of 3.8 into 10 raised to 26, 10 raised to 26 watts. So that's a huge energy, and whatever energy is delivered on the outside the Earth's atmosphere, it's around 1,370 watts per meter square, which amounts to about 5,000 trillion kilowatt hour per year. Now, I don't know if people are aware of the unit of energy, which is kilowatt hour. Just to briefly explain, 1 kilowatt hour would mean a load having wattage of 1 kilowatt. If it is operational for 1 hour, then it will consume 1 kilowatt hour. If the same load is used for 2 hours, then the consumption will be 2 kilowatt hours, so hence so on and so forth. So let us see how does the energy, the Earth's energy budget. I mean, once the incoming solar energy falls on the Earth, how much of it is actually usable and how much of it is not usable. So once the sun rays fall on the upper stratosphere, 6% of the light is already reflected from the stratosphere. Another 20% of the light is, reflected by the clouds. And when it falls on the Earth, 4% is already reflected from the Earth's surface. So whatever is absorbed by the land is only 51%. So if you keep panels, solar panels on the surface of the Earth, then this is the kind of energy, 51% of the energy is falling on the Earth, which can be readily converted from solar to usable energy using the solar PV panels. Then you can see, the clouds also absorb some 3% of the energy from the sun. Some is lost in the conduction. So all in all, only 50% of the light which falls on the earth can be converted into usable energy using photovoltaic cells. Okay, so this is a very important diagram. When you are talking about sun, you need to know, I mean, the movement of the sun from east to west is quite well studied, and people know at each day where the sun would be at a particular time. But of particular importance are 2 days, which are called as the solstice. So one is the summer solstice, which falls on the 21st of June, and there is a winter solstice, which falls on the 21st of December. On the 21st of June, which is the summer solstice, that is the longest day and the shortest night. And December 21st is the shortest day and the longest night, which means whenever a solar plant is designed, how much 1 kilowatt of solar PV system, how much will it generate? All the designing aspect depends on December 21st, because that is the shortest day and the longest night. As you can see, and then there are 2 other days which is marked as equinox. One which falls on the March 21st, which is 12 hours day, 12 hours night, and on September 21, which is again 12 hours day and 12 hours night. So all designing is on solar is based on what is the kind of power generation will happen on the 21st of December. As you can see, I mean, when I say 21st June is the longest day and the shortest night, you can see if this is the south and if this is the east and this is the west, what will happen on the 21st of June, the sun will rise from the backside, which is here of the horizon, and then it will set on the other backside in the west. So that is how the day is longest. And on 21st December, if you see, the sun will rise here. If you are standing here, the sun will rise here and will set here, which means that the day is very short. And December 21st is the most important day for designing any solar plant. So all the calculations are done taking into consideration at whatever latitude or longitude you are standing, what is the duration of sun hours. And then it is averaged out over the whole 365 days. It becomes slightly more challenging if the plant is to be designed in, say, belt of Konkan, which has 3 months of continuous rain. So during that time, the generation will be less. Okay, this is in the Indian subcontinent. What is the kind of solar insolation, which is the global horizontal irradiation on a flat panel? What is the kind of energy which falls from the sun? You can see, I mean, this is the Indian subcontinent. You can see that the global horizontal irradiation is quite high in Gujarat and Rajasthan area, in some part of central Maharashtra, and Andhra and Tamil Nadu. And there is a huge global GHI. You can see this is where Afghanistan is, and this is where Pakistan is. So you can see there is a huge potential for solar in Afghanistan, and that is why they are trying to harness the energy using solar. Unfortunately, since Afghanistan is a landlocked country, they have limited resources available, and since it's a very troubled country, they have to import almost 80% of the power from neighboring countries of Turkmenistan, Uzbekistan, Tajikistan, and Iran as well. So this is where they can, truly become Atmanirbhar and try to generate their own power. But there are a few challenges. One being, a security challenge. But they are trying to overcome that security challenge and trying to build a larger megawatt scale power plants. So it's a huge potential in India, in around Rajasthan, Gujarat, and Tamil Nadu. So that is why most of the plants in India are in these areas: Gujarat, Rajasthan, Tamil Nadu, Andhra, and some parts of Maharashtra. Like I presume this is somewhere is Dhule. So that has got a huge potential of solar. So this is where the plants are built, and will hardly find plants in the rest of the countries, basically in Northeast, because you can see that the Northeast potential is not that much. But then in Northeast, what is happening is they are not going into higher power generation, but they are trying to use solar street lights and all other equipments which they can use to complement their energy requirements. Okay, so there is, when you say the solar, you can have solar thermal, which is nothing but a solar water heater, and that parabolic solar mirror which you saw, that is also called as solar thermal. And solar PV. Solar PV will generally, not generally, it will generate, convert light into electricity, and they are semiconductor based materials with a band gap that matches the energy of the incident photon. Solar photovoltaic, since the cost of the material is high, it is slightly more expensive than the solar thermal. When you come to solar thermal, it converts the light to heat. And now how the light is converted into heat, it is through it depends on the absorptive property of the exposed surface. Now, for example, if you take a aluminium bucket and keep it on the terrace, the water is going to get heated up. So that is also solar thermal, but the absorptive property of aluminum is not as good as the materials which are used in solar water heaters. The technology is very simple, and the cost of the materials are also very low. And this is quite rampant in places like Pune and Bangalore, where the local municipality does ask the citizens to put solar water heaters on their roof if they want to get any permission from the municipal corporation. Okay, let's slightly go to more physics part of it. I mean, most of the students who are here know about the energy band gap. Probably they must have done it in class 11 or class 12. So in a insulator, why it does not conduct? Because the gap between the valency band and the conduction band is so high that no electrons from the valency band can go to the conduction band. Now let us come to the conductor, where there is no band gap, and the conduction band and the valency band are actually mixed together. So they are conducting even at room temperature. But in the semiconductors, there is a small gap between the conduction band and the valency band, which can be overcome if a suitable energy, the electron in the valency band, if it consumes the energy, suitable energy, it can hop to the conduction band. Now, in order to give a kind of example of photovoltaic effect, this is an energy, this is an electron which is in the ground state, which is in the valency band. A light of photon comes in, the electron will move from the valency band to the conduction band, and it will come back to its ground state, thereby generating energy. And then this process will go on and on and on. In the same analogy, you can see that the child is going up in an excited state, is coming down, is reached up, and is coming down, and again going up. So this is the kind of effect which happens. And because of the solar insolation, energy is generated. So because of the photons, voltage is generated. That is why it is called as a photovoltaic effect. So this is nothing but you can see from the valency band, a red photon will only reach in the mid of the energy band gap. The green photon will go to the conduction band and come back, and then the blue photon will go up in the excited state, and then this difference in the energy, difference between this and this is the energy generated. But the difference between the point, this point, and coming to the top of the bottom of the conduction band, this is, you know, it is generated, but it is more of generation of heat than generating power. So now solar cell efficiency, the theoretical limit is 33%, and photons with energy less than the silicon band gap, which I presume is 1.2 or 1.3 electron volt. So this accounts for the 18% losses, and photons with energy more than the silicon band gap are re-emitted as heat, and this accounts for 49% of the loss. So which is this one, this amounts for almost 49% of the heat loss. And current efficiency of the solar cell, which is a standard PN junction solar cell, is 21%. And when these cells are connected to each other in series and parallel, you make a solar panel out of it. And that solar panel efficiency is around 19%, because there is loss when you connect all the cells in series and parallel. There are some losses because of the interconnection. Okay, so now solar cell is nothing but a PN junction. So you have a N-type silicon, and you have a P-type silicon. You connect both of them, not physically. I will show you how it is done. When you connect together, then you have a PN junction. Now in silicon, I mean, addition of small percentage of impurities of foreign atoms in the regular lattice of silicon produces dramatic changes in the electrical properties. For example, antimony, arsenic, and phosphorus produces N-type silicon, because in the outer ring for antimony, arsenic, there are 5 electrons, and silicon there are 4 electrons. So 5 out of the 4 electrons from the antimony, arsenic, or phosphorus will latch in with the silicon, and 1 electron is free, which is, you know, ready to conduct. So this is how the N-type is made. Now the P-type is made by doping boron or aluminium, and boron, aluminium have 3 electrons in the outer orbit. So out of which, I mean, all the 3 will latch in with the silicon, and there is 1 left, and no, whatever is left is a hole. So this is how a PN junction diode is made. I mean, silicon solar cells are nothing but PN junction diodes, which are sensitive to light. So this is the working of a solar cell. You can see that this is a P-type semiconductor and a N-type semiconductor. When they are brought in close contact with each other, the electrons from the N side will move towards P-type, and the holes from P-type will move towards the N-type, and then you will form what is called as a barrier layer, which is this area is neutral. Now, once you apply voltage to the cell, what will happen is the depletion layer will reduce as the voltage increases, and once the depletion layer is completely vanishes, the PN junction will start conducting, which means that the holes from the electrons from the N side will move towards the hole. You can see from the P side, and the electricity is generated. So this is on the left hand side is a classic example of how the PN junction is made. You can see there is a base which is a P-type silicon on which the N-type silicon is grown, and then you have contacts on the top side, and there are also contacts on the bottom side to pull out the draw the current from the whole circuit. And you can see that there is a light falling on the solar cell. So this is general in a nutshell the diagram of a solar cell. So this graph, this photograph is also similar to what you have seen earlier, but you can see that there is a anti-reflection coating on the solar cell. Now, probably most of you who wear specs know that their spectacles come with anti-reflection coating. This anti-reflection coating is actually for a glass, for example, if the transmittance of the glass is 94%, and if you put anti-reflection coating on either side, on the inner side and the outer side of the glasses, the transmittance can go up to 97%. So a similar kind of strategy is applied in solar cells as well. They have an anti-reflection coating because they want to capture as much energy as possible, as much wavelength, as much as which is possible. That is why an anti-reflection coating is put on the top surface, which is exposed to the sun. Okay, so this looks like a standard IV curve. This is on the right hand side is a diode, and you have in the first quadrant IV curve. So what happens when you put without the illumination, if it is if the diode is connected to a circuit, you can get a simple straight IV curve, and it starts the current starts kicking in at say 0.7, 0.8 electron volt. So this is the point it starts conducting, and this is the time when the before this the depletion layer is decreasing. That is why it is not conducting. Now what happens if you illuminate? This is without the illumination. Now what happens if you illuminate this diode, which is a solar cell? What happens if you illuminate? Once you illuminate, you can see the curve is the same, but it has shifted. It is generating some current. Now what happens if the illumination increases? You can see that there is a shift in the energy, in the current. So there is the intensity is more, then the current generated is also more. So the current and the illumination are directly proportional to each other. Now, but then this IV curve is not depicted the same way. If you see any technical specifications of a solar panel or a solar cell, the IV curve is not shown the way it is shown here. It is usually shown this way. Now I would ask the students to find out why the fourth quadrant of the solar cell is shown as the first quadrant. So that's probably an kind of homework the students have to do. So this is an IV curve of a solar this is the IV curve. So you can see this is the short circuit current, and this is at the bottom is the open circuit voltage. So this is the IV curve, and then if you calculate from the current and the voltage, if you calculate what is the power, this will be the power. This will be the power curve. Now, what do you mean by open circuit voltage and the short circuit current? So open circuit voltage is basically when the two terminals of the solar cell are open, and if it is exposed to the sun, and if you measure the voltage across both the terminals, then you will see some voltage coming out. There will be no current because there is no load connected to it. solar cell will only generate power if the loads are connected, otherwise no. And then this is a short circuit current. When both the terminals are shorted, I'm sure it is going to go fut, and then that is a short circuit current. So this is the power curve, and most of the solar power plants and solar cells work in this region, which generates the maximum power. And all the electronics in the inverters and any other charge controller try to harness this energy, which is the maximum energy which is generated by the solar cell. Sorry. Sorry for the interruption because, okay. Okay, now, silicon solar cells are, manufactured from sand. Now, sand all over the world will have some quantity of silicon in it. And it depends what is the concentration of the silicon in the sand. So this is nothing but, silicon is extracted from the sand, and these are some silicon nuggets which you have here. Then they are melted in a furnace, which is called as a Jochalski method, and then you form a. So this is the silicon which is melted, and you find a cylinder which comes out of the formation in the furnace. So this is the cylinder which is of silicon, and then you dice it. Which you dicing is nothing but cutting it into small pieces. When silicon technology started sometime in 1980s, I mean commercial application, the silicon solar cells, the thickness of the silicon solar cells were of the order of 700, 800 microns. Now, at present, the silicon cells are diced with a thickness of 150 micron. So for the same material of silicon, you have now 7 times more or 6 times more silicon cells which are generated. So this is a furnace in which the diffusion happens. Once the silicon cell is made, if you want to dope it with antimony or arsenic or any other doping in order to form the PN junction, the doping is done in this kind of furnace. And this is a solar cell. Now you can see the earlier solar cell, the earlier cell which I showed you. This is used more into the semiconductor industry, and this kind of solar cells are more used in solar industry because the packing density is quite high for this kind of solar cells. Means more solar cells can be fitted into a particular area without causing a lot of free space available. So this is the front contact, and these are the back contacts. You have to take out power from the solar cell. Okay, now the IV of the solar cell and of the solar array. Solar array means some cells connected in series, some connected in parallel to make a solar panel. So now you can see on the left side, you can see that the solar cell, the IV curve is the way it is shown here. Now, when two solar cells are connected in series, which means if they're connected in series, then the voltage increases. You can see from 0.6 volts. The current remaining the same, it has increased to 1.2 voltage. Now, if they are connected in parallel, which means two batteries, if they are connected in parallel, then you get more current. So the 0.8 ampere current increases to 1.6, but the voltage remains 0.6 as shown here. Now, if both two cells are connected in series and two connected are in parallel, then what you see that there is an increase in the current as well and an increase in the voltage as well. So this way, more cells are connected in series and parallel in order to make a complete solar panel. Now, once the series and parallel cell connections are made, these solar panels have to stand the test of weather for 25 years. I mean, these are what the solar panels are. This is the standard lifetime of the solar modules. So then, which means that they have to be saved from the atmosphere. So that is why what is the front side of the solar panel is a glass which has a high transmittivity. It is actually more than, it should be more than 95%. Now, if you can see, this is a solar, this is a array, solar array, where cells are connected in series and parallel. Here, I think there are 16 connected in series, and two such series are connected in parallel. You can see that there is an output terminal coming in here. In order to save the solar cells from the test of time of the weather, they are actually encapsulated, which means there is a ethylene vinyl acetate sheet which reduces or stops the seepage of moisture inside the cells. So there is a EVA sheet at the top and the EVA sheet at the bottom. So the solar cell is sandwiched between two EVA sheets, and then there is a rear Taylor sheet to stop the backside reflection, because if the backside, if you assume, is black, then what will happen that the heat coming out from the ground will also be absorbed by the solar panels, and the solar cell, the solar panel might get heated up. So that is why a rare sheet is given, which is usually white in color, in order to reflect the sunlight. And the most important use of the EVA sheet is also for high electrical resistivity. Okay, so this is the kind of family of modules. You can see modules come in different shapes and sizes. So when I started sometime in 2009, the highest module size was around 200 watt peak for solar PV power plant application, and now the solar panel size is a 500 watt peak. So this is a 500 watt peak panel, and this is a 250 watt peak panel. So this the 500 watt peak panel will generate 500 watts of power at a given time. So now, coming from solar cells is a very different technology, but that is more of a science problem. But when you come to a solar power plant, it is more of a engineering problem. So once the solar panels are made, then you have to connect them in series and parallel, and you have to generate power, because I'm talking more about the power generation plant. So what are the components of the solar power plants? One is a solar PV panel. Power from the solar panels are DC, and what we consume in our houses are AC. So we have to convert DC power to AC power. So that is why the inverters are required. So this will be another assignment for students to find out why solar PV panels generate DC power and not AC power. That could be used as a home assignment. So Inverters is the heart of the solar PV plant, which converts DC power to AC power. Then there are junction boxes which are required. When the solar panels are connected in series, say for example 20 panels are connected in series, and you have to connect 3 such string of solar panels in parallel, then you require a junction box where 3 series will come in and only 1 will go out to the inverter. So junction boxes are required. Now mounting structures, I mean solar panels have to be mounted on some kind of a rack or some kind of steel structure. So mounting structure is also a very important part of the solar power plant. And then there is a balance of system. You need cables, you will need circuit breakers, you need fuses, you need protection devices. So all this are the components of a solar power plant. So now, once you design the solar power plant, what are the various aspects? One is the electrical aspect. So you have to do because since the solar panel generates only DC power, you have to do a DC side design also. You have to do an AC side design also after the inverter. Now, since this is even if it is a field-based plant, then some kind of civil design is also involved. Then there are, since you have a mounting structure, the structural designs also form a very important aspect of the solar power plant. Now, the biggest advantage which I personally had in all these things. I'm a scientist by education and qualification, but I have a base in science. So more so for students who are doing physics or who have done physics till 12, some kind of idea you will have when you see an electrical design, a civil design, and a structural design. The structural design is more got to do with classical mechanics. If you study classical mechanics, and this kind of things are seen. So the advantage of a science graduate over an engineer is that you can have a crux of all these 3 aspects. If you are an engineer, then you are either an electrical engineer or a civil engineer or a structural engineer. So you know only your part of the work. But a science graduate can know all the 3 aspects of the power plant. So these are the various aspects of the solar power plant. Okay, now this is a single line diagram. So when a solar power plant is, the circuit diagram has to be shown. This is nothing but a circuit diagram, which when you do 11th, 12th physics practicals, you also have a circuit diagram. So this is also a circuit diagram for a solar power plant. You can see on the extreme left here and on the extreme right here, there are solar panels. There are some solar panels which are connected in series. In this case, there are 20 panels connected in series, and there are 4 such series. So which comes to the junction box. So all the power from the DC from the solar power plant is collected by the array junction box, which is just nothing but a junction box. And from here, only one cable goes to the inverter. So inverter will connect, this side is DC, this side is AC. So the inverter will convert the DC to AC, and then through various protection circuits, it goes to the control panel of your house or your factory. And from here, the loads are connected, your factory loads, your home loads are connected somewhere here on the bottom side. And then that's how the power is then consumed by the loads. So now this is a typical, I'm sure the students might not even understand what is this, but this is like a foundation of a solar PV plant structure. This is like a cylinder, which probably whenever you are seeing the metro works being done, you can see a huge, very large cage of steel being inserted in a hole which is made by the drill. So this is something like this. So there is a lot of design aspects also involved in this kind of civil designs. So this is a very interesting. This is a solar PV module mounting structure. Now, what happens? Although one might say that this is just a steel mounting structure and not lot of construction, lot of design is involved, but this is the most critical part of the whole design. What will happen? These are usually mounted at some angle between. In India, it is between 7-8 to around 35-36 degrees angle. Now, what will happen if there is a wind? If you are in an open field and if there is a lot of wind gushing in your power plant, since these are at an angle, what will happen is the wind will try to uplift the whole structure from the base, from the ground, and in that way, if your design is not proper, then your panels are, the whole structure will come out from the earth and the panels will be lost. I have an example where I was constructing a 10 megawatt power plant in Bikaner, and the design was proper, but the connections were not made properly. When the engineers were making the connections of the mounting structure, there was a huge gust of wind which was coming in, and all of us then entered into the control room, and that day we couldn't go out. The next day morning, what we saw was the whole structure along with the solar panels. They had all being pulled out of the earth, and we could not even see where the panels are. I lost around 50-60 panels. So the design of the solar mounting structure is quite important, and this is done by using finite element analysis, nothing but a part of classical mechanics. So once you do the finite element analysis, this is the output. You don't need to understand how it is done, but you can see at 200 kilometers per hour of wind speed, there is a maximum displacement of 36 millimeters, which is on these edge points. Since the design was done properly, you can see that the displacement at the bottom columns is very low, which means even if there is a wind speed of 200 kilometers per hour, the columns are going to remain in the foundation, come what may. If the wind speed goes beyond 200, then nothing can be said. But then this is the kind of displacement at 200 kilometer per wind speed on the edges. So care has to be taken that this kind of 200 kilometer per hour wind speed are once in a lifetime event. But when there is a once in a lifetime event, your panels have to still withstand that kind of force. So then the design aspect of the mounting structure becomes quite important. So now this is just a very small power plant. If you want to design an off-grid power plant, which I'm sure the students who are here, who have done basic physics in 11th and 12th, can design this kind of power plant. So this is just a load pattern. You can see there are a few lamps and few LED, some loads which are given here. You can see that the third column is what is the wattage of each lamp or each LED. How many quantities of this kind of lamp and LED lamp and fan, whatever loads. What are the numbers? You can see the total watts. So total watts is nothing but the multiplication of a quantity and the wattage. So you can see the total watts here. You can see it is 42,432 watts, which means 42 kilowatt. Now, this is only in terms of watts. But what we are going to generate is not watts, but it is going to be watt hour or kilowatt hour. So you need to know what is the duration of this lamps with these loads are going to be used. So you can see this column shows you the loads, duration of the load. So I have considered it as 4. So each equipment is working for 4 hours. It could be all at the same time. It could be in any random operations. So this is the watt hour or kilowatt hour. So which is nothing but watts multiplied by hours. So that is a watt hour. So this is the total watt hour requirement, which is nothing but 169 kilowatt hour. So this is the requirement of one particular load profile, which is shown here. Now this is designing. I mean, this is just in a nutshell Excel sheet which I have made. So here the 24 hours would mean one day, which would mean 4 hours today, 4 hours tomorrow, which means that you need to have an autonomy. Autonomy is nothing but if there is no sun tomorrow, then will the power plant with the battery be able to generate and store and that kind of power in the battery? So I have taken it as one day, because if the autonomy increases, then the battery size increases, solar power plant increases, and all other aspects also increases. So supply watt hour is what we saw in the earlier slide. It is 169 kilowatt hour. The depth of discharge. See, the battery is 100%. You cannot discharge it to. You can discharge it to 100%, but then the life of the battery goes down. So it is better to store some energy in the battery. So depth of discharge is usually taken as 0.8, which is 80% of the power from a battery you can use, and 20% has to still remain. So 20% is unusable, you cannot use it. And the control circuits which are used will see to it that the battery is cut off when the depth of discharge of 80% is reached. Then these are the various efficiencies: battery side efficiency, battery efficiency, AC side efficiency, DC side efficiency, and what is the battery voltage, because one battery is usually 12 volt. Even if you have 2 volt cells also, but I have considered 12 volt battery because that is what is normally available, and with some kind of ampere hour. So 12 volt, 100 ampere hour. I think the car batteries are 12 volt, 20, 30 ampere hour. So this is this PSH, that is the solar insolation, which means if solar incident photon energy falls on a 1 kilowatt power plant, how much of the energy it will generate towards the end of the day. So here I have taken it as 5.5 because that is the average which is calculated all over India, which means that a 1 kilowatt system, 1 kilowatt solar PV system will generate roughly 5.5 kilowatt hour, which is the usable energy. And these are again cable losses, charges efficiency, and if you put that in an Excel sheet, then you will see that the total solar panels required to generate energy for this kind of a system would be around 49 or 49 kilowatt. The batteries required will be 452 of 112 volt 100 ampere hour battery, and 250 watt peak panel you will require around 200. So this is quite a huge power plant, but this kind of huge power requirements, usually people don't go with batteries because the batteries become quite expensive. If a standard normal solar power plant without a battery costs 100 rupees, then with the battery for 4 hours of backup, the battery, the whole system cost would go up to more than 140 or 150 rupees. So this is just an example of a solar 5 megawatt solar power plant which I had constructed in Chandrapur in Nagpur. So you can see there is a civil foundation here. There is a module mounting. This is the module mounting structure, and these are the this is the link because I was doing a seasonal tilting. I wanted to tilt the angle of the panels once in a year, twice in a year. So I had that tilting. So in order to harness more energy, you can see the same. I mean, you can see the panels as well now connected. This was during the construction side. You can see the panels were quite dirty. This is the 100 kilowatt rooftop structure, which was also made in Nagpur. You can see there are a whole lot of panels which are connected. Some are connected in series and parallel. Again, you will have foundations for the module mounting structures. So this is a photograph of an inverter from DC. You take the power, you convert it into AC power. So this is an example of an inverter. This is a junction box which takes all the power from the solar and gives it to the control panel or circuit board of your home or your factory. So this is just an example of an off-grid village electrification project which I had done in the Western Ghats. So this village had around 60 houses. Until 2016, they did not have power till 2016. So we had constructed a small 10 kilowatt power plant, and we had done the complete electrification using transmission cables. All the power was transferred from the solar power plant to all the houses, and we had done the internal connection as well. You can see that the houses are very pakka houses, but they don't have power. So now, once the power has come in, some kind of industry has also started. I mean, a small rice mill has also started because people had to go almost 20 kilometers to grind the rice or any other food grain items. So now there is a rice mill also which is started in the village. So and here we are that the solar power has lit up a bulb in a house which is from the same village in the Western Ghats. So we have now traveled from the sun to the light here in the house. That's about it. Thank you. Questions are welcome.
Dear student, if you have any question, you can ask. Sir, there is one question from one of professor from physics department. What is the maximum efficiency of solar cell in India as well as in?
See, the maximum efficiency of solar cell right now. I mean, there are two parts. One is the solar cell, but
Okay.
when you're constructing a solar power plant, you cannot consider the efficiency of the solar cell. You have
Okay.
to consider the efficiency of the solar panel. So
Panel,
right now
okay.
it is around 19% solar panel and 21% for the solar cell. Because there is a loss between 21 and 19 because of the interconnections which are made. And the biggest killer, just for understanding, a 500 watt panel ideally should generate 500 watts.
Okay.
500 watt hour in 1 hour. But what happens is the silicon the silicon solar cells are susceptible to temperature. And these panels are tested. When you say 500 watt, it is tested at 25 degrees centigrade and 1000 watt per meter square. Now what happens is, but this is a very ideal condition. But if you go on the field, you will never get 25 degrees centigrade and 1000 watt per meter square. 1000 watt per meter square is usually in the afternoon at 12 o'clock. So what happens is in the morning, say for example, in a place like Rajasthan, when the ambient temperature is going beyond 50, the panel temperature can easily cross 65. What happens is there is a degradation of power for every degree centigrade of, I think, around 0.15% per degree centigrade beyond 25. Now it is, if the panel temperature is 65, so difference is around 40 degrees centigrade. So 40 degrees centigrade multiply by the percentage 0.2. Let us assume 0.2 for easy calculation percent. So there is 8% loss of the power at 12 o'clock with 1000 watt per meter square. This is one scenario. So the second scenario is in the morning, say around 8 o'clock. The temperature of the panel might be 25 degrees centigrade. But the insolation, that the sun irradiation, is not 1000 watt per meter square. So which is probably 200, 300. When the sun rises, probably it is 100, 150, 200 watts per meter square. So there is a loss there as well. If you draw a graph of the time of the day in the x-axis versus the power generated, energy generated on the y-axis, you will have a perfect Gaussian curve, which means at 12 o'clock only maximum power you will get. So when you design a power plant, what happens is, if you are, if you have solar panels of 50 kilowatt, then the system will not generate 50 kilowatt of usable energy, usable power. It will generate probably 20, not probably, generate 20% less. So a 50 kilowatt DC power plant will generate only 40 kilowatt AC. And throughout the day, the power plant, 50 kilowatt power plant will generate around 200 kilowatt hour. So
Okay. And one more question is there.
Can I interrupt a minute?
Yes. Yes. No.
There is a second part to this workshop on which sir is also going to explain about the calculating and how to build a small power plant. So I request everybody not to, the students and the participants not to leave. Okay.
Yeah. So probably should I start, because then I will quickly run through it.
Okay. Fine.
But I will quickly run through.
Yeah. And then we can take up the questions. Okay. Yeah.
Yes. Yeah. Thank you, Sudesh sir. Thanks.
I mean, I presume since there are no questions asked by the students, so I can only assume either they have understood everything or they have not understood anything. That is why the questions are not coming.
Sir, in chat box there is one question: why we cannot harvest infrared waves?
Right now, the technology which is available. I mean, to answer his question, why we cannot? Yes, we can. Yes. But then the material used for the silicon, material right now used is silicon. So silicon cannot, consume, or it cannot absorb infrared. It can absorb infrared, but then there will be no effect on it. It's basically the band gap which is very important.
Okay. Yes. Okay. Can by decreasing bandwidth or band gap energy, can we enhance efficiency?
Okay, I will come to that point.
Okay.
See, right now, silicon solar cells can have an efficiency of 21%, which is, if you see the solar spectrum, like if I can go to that solar spectrum. See, the silicon solar cells are probably only consuming, converting, not consuming, converting only this small part of solar spectrum to energy. Now,
okay.
If you want to increase the efficiency, yeah, of course you can do that. Now, what will happen is, there are examples available. It is not commercial, but it is available. You can use the whole spectrum from blue to red So you have multi-layers of multi-layer junction solar cells, which will absorb the whole spectrum, and the energy efficiency of these multi-layer solar cells is around 40 to 43%.
Okay.
But it is commercially not viable right now. This is used in space applications where the energy the energy is important, not the cost. But in the terrestrial applications, energy is important, but at what cost? So for space applications, I mean, solar cells also started commercial applications from space applications only, and then they came when the cost became very, cheaper. Then they were used for terrestrial applications.
Okay. Can I take one more question from student, sir?
Sure.
Yes.
Sure.
There is one more question from Satish. Sir, can we add filters on solar panels so that suitable amount of energy provided to solar panels and no loss or any extra generation of electricity takes place?
See, solar filters are used. Filters are definitely used. They are used for more like ornamental purpose. Like for example, there is something called as a building integrated photovoltaic, BIPV, where generation of energy is important, but then the building should not lose its aesthetic value. So the filters are used there also. The filters, to answer this question, yes, you can use the filters as well.
Okay. Sir, I'll take one more from Dr. Rajesh Raut. Can we use optical fiber to catch sunlight and send it to photocells to store safe cool place?
Optical fiber to direct the sunlight on the solar cell. I mean, what was the question?
Can we use optical fiber to catch sunlight directly? Can we directly incident sunlight to on optical optical fiber entrance?
Yes.
And then we can convert that sunlight into for our electricity purpose.
No, but then how would you do that? I mean, if you trap the solar in a fiber optic cable, and if you want to expose why would you do that? Okay, one is why would you do that? Because you want the whole panel to be exposed to sun. And optical fibers probably have a limitation on the size.
Yes, correct. Due to the core size.
Use that.
Yes,
I mean, it can be used if it is a smaller. I mean, I'm talking more about the commercial point of view. But ideally, yes, you can use.
Yes,
Commercial application probably it might not be, cannot be.
Due to the core size of optical fiber.
Yes, correct.
Yes.
Unless you have a larger pipe size optical fiber.
Yes. Thank you, Rajesh sir, for your nice question. Yes, sir, you can proceed for next.
Okay, so after we have gone from to infinity and beyond, I will give you a basic example of how to design a solar PV plant. I mean, for this kind of design, you need only education probably up to 10th up to 12th, and you need a lot of common sense. If you have these two, you can design a power plant. So this is a part of a course which I usually take for the students in the university in Afghanistan. So this is the outline. I mean, these students are engineers as well as they are from a pure science background. So this is the outline of the course. I mean, this is the outline of the whole presentation. We'll talk about the system configuration and operation. What is the scope and application? What is the design procedure? How will we select PV panels, battery? There is something called as a controller, which controls. A controller is nothing but which interacts with one part and two parts, and there is a controller in between. So it is like a controlling situation. So I will give you I probably might not give you a design example because then probably it might take another 3-4 hours. system integration and what are the challenges. So this is a very simple direct DC load. You connect the PV module to the DC load. The DC load could be a simple water pump, a small water pump in a small field, which is, pumps come in DC and AC both. If it's a small DC pump, then you can connect directly PV modules to the DC load. Nowadays, if you go to the countryside and if you see fields, you will see solar water pumping plants, so usually 5 kilowatt and above. So this is just an example of that DC loads, which is a water pump. Then there are some DC loads whose voltage here is different from what the PV module might give. So for example, a 500 watt peak panel has an output voltage of around 40 and around 12 amperes of current. So roughly 40 amperes and 12 amperes of current, which means 12 fours of 48, so 480 watt peak. So now, but if the DC load has a input voltage of say 12, then if you connect the PV module directly to the DC load, then you are going to surely burn the DC loads. So then there is a DC to DC converter which is needed. The input of the DC converter probably is 40 volts. The output is 12 volts. So this is how a DC to DC converter will work. A DC to AC converter is nothing but an inverter which converts DC power from the module to AC. So here it is DC, here it is AC. So DC to AC conversion. Now, this application could be large AC pumps again in the fields. We can see 5 kVA pumps. Sorry, not 5 kVA. 5 HP pumps and 10 HP pumps, which are seen on the field. They usually work this way. So this is now you can also put a battery in between the DC load and the PV module. These are miniature applications, pocket calculators, watch. Once you put the light on, because they're very sensitive, when you put the light on, the batteries, the solar cell gets activated, and you can do whatever calculation you have to do with the calculator. Now this is the charge control. This is a charge controller. What is the application? It is usually used in mobile towers. Earlier, till probably 2013-14, all the mobile towers, each tower if you see, any mobile tower if you see anywhere in the world, each tower has a load requirement of 15 kilowatt, and this 15 kilowatt can be you can use a grid to power up this 15 kilowatt. You can use a DG, which is usually seen in the mobile telecom towers, or you can use the solar also. So right now what has happened is the telecom towers are moving from AC to DC. So all the loads are now DC. So this is how the PV module controls the voltage and the power from the controller controls the power from the PV modules and gives it to the battery, which in turn goes to the DC loads. And this is how the small home lighting systems also, small home systems also work. So this is this and this are same, but this is a standalone system. Like for example, in the villages which I just shown in the Western Ghats, that is not connected to grid even probably 2019 when I last visited the plant. So it is still not connected to the grid, which means it is an off-grid standalone system. So this is how the standalone system works. Okay, this is an off-grid grid independent or standalone system. Now what happens is, so this is a PV array. It is going to the charge controller. Charge controller goes to the battery bank. And then if there are DC loads, it is connected directly to the DC loads. And if there are AC loads, the battery is connected to the inverter. And to the distribution panel, it goes to the AC inverter, AC loads as well. So this is again a similar system, hybrid system with both DC and AC loads, basically used in some kind of hospital, because I had done one, what do you say, a 40 kilowatt hospital, a project for an hospital in Bangalore, where they wanted to connect all the loads of the hospital to solar, leaving aside only the operation theater, because that is not what they could connect to solar, because if sometimes if there is a failure, and failures do happen in electrical systems. So if there is a failure and if there is an operation going on, then what is the kind of eventuality they might face. So this is right now, this is a grid supported, grid dependent system. Now what happens is, a solar PV plant, there are two kinds of solar plants. One is an off-grid and one is an on-grid. On-grid means it is supporting the grid. So for example, if there is a solar power plant which is connected to your loads through a control, to a distribution panel. So you have a grid connected to the distribution panel. You have a PV solar system also, which is connected to the distribution panel. And this is a battery bank, which is used usually for some kind of emergency backup. So what happens? These kind of systems will be operating. Since they are grid dependent systems, these kind of systems will be operational only if there is a grid available. If this connection, if this point is disconnected, then the whole PV system also will not work. They are designed in such a manner that the inverter trips once there is no grid. So these kind of systems are usually used in places where the cost of the electricity is quite high. For example, in Mumbai, in the place where I stay, I am serviced by BEST, and my per unit cost, so total per unit cost is around 12-13 rupees per kilowatt hour. Now, if I have a big house here and if I want to reduce my power electricity bill, what I would do is I would connect a solar power plant which is grid connected. So in the daytime, I will consume whatever energy is generated by the solar in the day, and in the night time when there is no sun, I will use the power from the grid. This way, and since the energy is charged from on the time of the day, so if you consume power energy in the afternoon, the cost probably would be around 12-13 rupees. But the same energy, if it is used in the evening, then it probably might be 6 or 7 rupees. So what people do is to shave off their electricity bill. They will put a solar PV plant. They will shave off their power cost in the daytime, and when it is evening, they will consume the power from the grid. So this is how these systems are designed, and it can also happen that in the daytime when you are generating power, your loads have gone down. Just for argument purpose, if your power plant is say 50 kilowatt, generating 50 kilowatt AC, and if your loads are only 40, but the system, since it is a grid connected system, the solar PV plant does not understand that the loads have reduced. So what it will do is it will generate still 50 kilowatt, it will the loads will consume 30 kilowatt, and the rest of the power, which is 20 kilowatt, is supplied to the grid. So that is how the energy. I mean, then their power utility will. I mean, some kind of special meters have to be connected, which will record from the solar to the grid and grid to solar. Usually, what happens? Our meters are connected in such a manner that they only record from the grid to the load. But then this energy meter, special energy meters, they record both ways, from the solar to the grid and from the grid to the loads. And then they will find out how much you have generated, how much you have consumed, and depending on that depending on that, the billing is made. So this is this kind of the system. This kind of system are available throughout the world. Throughout the world, I mean, most of 90% of the plants in India are using this grid dependent PV solar system. So, okay, the off-grid system configuration and operation. So DC, as you all know, I mean, as we know, DC energy is produced by the PV array and is used to charge the batteries via the charge controller. DC appliances can be connected to the battery via fusing. Some controllers, I mean, voltages can be typically 12 volt or 24 volt. Each battery is a 12 volt battery. If you want a 24 volt system, then you have to connect two in series to make it 24. And these kind of systems are usually used for solar home lighting systems. And sizes would be larger than 1 kilowatt. And this is a typical energy flow of an off-grid system from the solar panels. From the sun, it goes to the solar panels, and through the disconnect switch goes to the inverter, and from the inverter to the AC breaker. So you could also have an additional source of generator, so which is connected here. And then energy metering in and out both could be connected. If it is a off-grid system, but still you can connect it to the grid. So this is a typical a line diagram for a standalone PV system with only a DC output. So the modules are connected. Module positive and negative are connected to the positive and negative of the controller, and then the battery is also connected to the positive and negative of the terminal, and the DC loads are also connected the same way. So the controller will control the the power from the module to the battery and then to the DC load. Again, this is a off-grid PV system, DC out, DC both. I mean, DC and AC output as well. So this part is from the DC side, and then you put an inverter here, and then you invert the power. Sorry, and to make from DC to AC, and then supply the power to the AC loads as well. The scope and application and cost. And first you have to make a decision whether you want an autonomous or an islanded PV system. I mean, it can have various applications like remote housing, water pumping, security, whatnot. Everything you can have. Now, what is required is a geographic location, because energy, the sun solar insolation in Mumbai and solar insolation probably in Delhi is quite different. So that geographic location has to be kept in mind when you design a solar PV system. Now, I mean, solar power plants are usually warranted for 25 years. And that way the maintenance is quite low because there are no moving parts. So the maintenance is quite low. Only some kind of preventive maintenance definitely has to be done. Upgradation is all usually required because your house if you have a 2 kilowatt system, your family members grow, number of rooms increases, then you have to also upgrade the system, and that is all usually required. But in terms of, but when it comes to the grid, if you don't have a solar system, then you don't need to upgrade because the grid is already there to support. The PV module cost usually is around 35 to 40% of the cost of the solar system, and this system's cost is of the range of 1.5 to 2 lakh rupees per kilowatt, but this is slightly old prices. They still have gone down slightly now. So what are the design steps? When you design a solar PV system, what are the steps here? First, you have to understand what is the customer's requirement. So, I mean, usually the client will say that, I want a 4 kilowatt system or a 5 kilowatt system. I don't know. You have to analyze what is the requirement. Second is site survey is required. So if you have a terrace and which does not have any tall buildings in the surrounding, then it is good. But if you have the solar panels are usually inclined, not usually inclined, they are always inclined facing south. If this is facing south, and then your left side is east and the right side is west, there should be no hindrance of anything which will cause a shadow from on the solar panel. So there should be no hindrance on the east, south, and west. Even if there is a shadow, the shadow has to be farther away. How farther away? It should be so farther away that that building or that tree will not cause a shadow on your system throughout the day. So that site survey, this is one. Second is, if it is a rooftop mounted, because since they are small power plants, they are usually rooftop mounted. When you see the roof, you have to also evaluate if the roof can take the load, physical load, weight of the whole power plant. Usually, this kind of power plants will have a load of around 30 to 30, 25 to 30 kgs per square meter. So a structural assessment also has to be done, which means then you have to speak to the architect or the owner of the building, and he has to get it checked from his structural engineer whether this kind of weight is allowed on the roof. Third is the solar resources and environment evaluation. Solar resources means how much solar irradiation is falling and that particular geographic location. Because when you construct a solar power plant, the client is going to, or the user is going to ask you how much power, how much energy I'm going to generate. So for that, the solar resourcement, I will just show you an example as well, what kind of solar assessment needs to be done. And environmental evaluation means whether it is going to rain, how many months it rains, what is the dust seen in that area. If there is a lot of construction going around, then there is a lot of dust which is generated, which falls on the solar panels, and then a regular cleaning of the panels is required. So this kind of evaluation also needs to be done. So you have to determine the load, power, and the energy consumption. I just gave you an example of load, power, and energy consumption, how needs to be done. So system concept development. Okay, now in this, you have to make a judgment. You along with the user have to make a judgment is what kind of system is needed. Whether you require a completely off-grid system, which means you don't want to connect to any grid infrastructure, or you want a grid system where during the daytime you will shave off the power coming in from the grid, and in the evening you will take the power from the grid. Since we are talking about, if we talk about batteries, then you need to understand what is the select what is the battery capacity, what is the PV size array, and then you have to design a single line diagram. That is basically a circuit diagram. And then you have to, of course, verify the battery sizing, the charge controllers, and you have to select the balance of system, mean the structure, cables, and then you have to optimize the design. Okay, now the customer requirement analysis. We have to do an assessment of the user requirement, cost, time scale, and space constraint. Now, when the client says that he requires a power plant of 5 kilowatt, you will have to see whether that kind of shadow free space is available. A thumb rule for this kind of power, designing such kind of power plants, is that for every kilowatt you require 8 square meter of area. So now, if the client says that he wants 10 kilowatt or 20 kilowatt is available, I mean, can be constructed. Second is the cost, because higher the size of the equipment, higher will be the cost. And third is the user requirement. You have to really find out what is the energy consumption. Probably you will have to do some, put a tongue tester to measure the currents throughout the day to find out what is the actual consumption. Okay, so loads are different in day and night time. Probably there is no one at home in the daytime, then probably there are no loads, which means the solar power is going to go waste. So that has to be saved in the battery. So if there is no one at home, then in the night time probably there will be huge loads connected. What would be the critical loads? For example, if you have a server in your office, which needs to have power 24/7, then that calculation also needs to be, considered. That kind of loads also needs to be considered. Battery autonomy. Battery autonomy means if the solar power plant will generate today, and you can consume it today itself. But what if there is, no sun tomorrow because it is raining? So that time you will have to say that, okay, I want a battery autonomy for 2 days, which means the solar system will generate today, it will consume today, and it will also save some power for tomorrow. But when you say that you want a battery autonomy for tomorrow as well, then your solar power plant size also increases, because you have to store much more energy into the battery. So solar power also, solar PV also has to be higher, which means that the cost goes higher. Okay, if there are any other resources available, which usually is not the case in India. I mean, some people do have a wind turbine. So whether they are going to share the power with any other renewable energy source. Seasonal requirement, that is also quite very important. For example, in Delhi, the seasonal requirement of AC will not be there in winters, but the AC requirement will be there in the summer, and vice versa. I mean, the heater are required in the winter, not in the summer. So that kind of seasonal load pattern, load requirement also has to be recorded. So it is a very simple job. I mean, you have to ask the client how many ACs are operational, or how many heaters are operational in the winter or in the summer when the ACs are operational. Future expansion, future expansion has to be like if you put it on the roof, and if the client has a plan to construct another floor on the roof, then it becomes pointless to construct a solar power plant. Availability and the quality of the grid. So availability, I mean, how often there is no grid trip off. This is what you have to find out. If there is an availability of the grid, then in order to shave off the time of the day energy, you can go to for a grid connected system. Otherwise, for a battery based system. And of course, there is a DG or not that has to be also taken into consideration. Okay. So now, in order to do the site survey and assessment, the latitude and longitude of the site is quite important. More than the longitude, the latitude. Because I think Mumbai is at 13 or 14 degrees latitude. So the panels have to be inclined, not a thumb rule, but it has to be inclined for maximum, generation of power. So if you are say probably in Nagpur, then probably the latitude is around 27 or 28. I'm not really sure. So that angle has to be maintained. Location, shape, size on the level of the roof. And of course, location comes with the latitude, shape. If it is a perfectly square or a rectangle, 1,000 square meter place versus if there is an irregular shape with 1,000 square meter, then the power plant which can be constructed on a regular shape will be much larger than what the power plant is constructed in an irregular shape terrace, because there is a lot of loss because of the irregular shape. The terrace and the roof orientation and the tilt. Now, if the shed is a tilted shed, then you don't have any other option but to install the panels on the same tilt. Orientation is quite important because your roof has to face south. If it is not facing south, then the structure has to be manufactured in such a manner that the solar panels will face south. Shadow analysis has to be done. So usually what happens is there is a plant, there is a solar panel in the front and there is a solar panel at the back. So once, throughout the day, when the sun is moving, the panel in the front should not cause a shadow on the panel at the back. If that happens, then there is a loss. I will just give you an example. So this you can see is a one panel in a fixed in a landscape orientation. There are 4 panels, 2 in the front, 2 in the back, and there is some distance. There is a pitch, which is the gap between the front edge of the first panel and to the front edge of the next panel. So that distance is now kept as 5 meters. Now let us see, and this is done on the right hand, left hand side. You can see it is on the 21st of December. The shadow analysis has been done. Now let us see the shadow analysis. I presume everyone can see the video. You can see there is a remnant shadow falling on the panel. And then in the evening, definitely there will be a shadow, but in the evening, the generation also quite less. So you can see there is a remnant of a shadow, which is not good because it will not generate maximum power. Now what I will do for this shadow analysis, what I will do is I will increase the pitch between this panel and this panel. Right now this is 5 meters. I will make it 7 meters. You can see it has gone. You can see the time also here. There is no shadow throughout the day on 21st of December. So I will keep a pitch of 7 meters for this kind of system. Sorry for the mishap. Can you see? Just a minute. I mean, Bilin, can you see?
Yes, yes, we can see.
Yeah, but then I think it is not going into the presentation mode.
Sir, 2 minutes, sir. It's okay now.
Yeah, but then this is not the slide which I wanted to show. Yeah, this. Yeah, sorry. Yeah, this is the. Sorry. Okay, so I just showed you the example of shadow analysis. So that is very important because if you are spending some money, you have to get maximum benefit out of it. Okay. Now the next comes is the static load bearing capacity of the roof. That's what I told. I mean, whether the roof terrace will be able to take that kind of weight load on the roof. Height of the parapet wall is quite important because if you are going very close to the parapet wall, then the parapet wall also will cause a shadow on your on the panels. So a thumb rule is whatever is the height of the parapet wall, that much space you leave between the parapet wall and the front edge of the panel so that there is no shadow. Cable duct. So now, since the systems are usually installed on the terrace, how will you take the power cables from the terrace to the control panel, which is usually on the ground floor? You cannot just throw the cables from the terrace and it directly goes. So you have to see whether there is a cable duct availability. If not, then you will have to make that kind of cable duct availability. So electrical distribution box location. So I mean, usually you will have to give the power from the solar panel to the control panel. Now, where is the location of the control panel is quite important because the cable length is important because of the cable length, the cost increases, might increase, might decrease. That is one part, and the second part is if the lengths are shorter, then the cable losses are less. That you have to keep it in mind. Load, whether there are single phase loads or three phase loads. Load energy metering. I mean, that's as I told you. If you are going to have a grid dependent system, grid connected system, then you need to have a what do you say? Net metering system. Access to the roof. It's quite important whether there are staircase available to go to the roof, and architectural and regulatory requirements. Does the municipal is there a requirement for regulatory permissions to be taken from the local authority if you are constructing a power plant? Electrical regulators also, like the state electricity board and the municipal corporation also. If that is required, you need to take that before you construct the power plant. Okay, so this is a solar resource and environment evaluation. I mean, detailed solar resource assessment of the PV system, design month, optical tilt angle, orientation of the PV plant that is required. What is the minimum and maximum average ambient temperature? What is the maximum wind speed and direction? Because that is also quite important. As I showed that the whole structure can be uplifted if the the speeds are not considered. Third one, and the third one, which is the last one, which is very important. Birds, animals. Birds usually have a tendency to sit on the top edge of the roof. And once these birds sit, because of the bird poop, a lot of cleaning needs to be done. One is cleaning, and the other is there is a loss of power if there is a bird poop on the panel. So, and then PVC simulation, that is a simulation required, but then for smaller systems, the simulation is usually not required. So this is the solar resource data. You can see this is for a latitude 18.5 and longitude 73.9. I think this is somewhere near Pune. This is for from January to December. This is the solar insolation. Just don't look at the first four rows. Look at the fifth row from the tilt 0, 3, 18, 33 and 19. This is the solar insolation, which is kilowatt hour per meter square per day, which means, for example, if there is a 1 kilowatt system in Pune in this location, and if it is at an angle of tilt angle of 0, then it will generate 5 kilowatt hour. 0 means it is completely flat parallel to the ground. And then it will generate 5 kilowatt hour in the month of Jan. 5 kilowatt hour per meter square per day. Now let us see the tilt. So you can see from tilt 0 to tilt 3, the insolation has increased. It is still increasing, and it is 33 degree at 33 degree tilt angle. The insolation is quite high, but 33 degree angle will require a lot of wind speed calculations. So usually the tilt angle, latitude tilt angle is considered, which is around 6.1 kilowatt hour per meter square per day. And if you see on the extreme right, there is the average, annual average. In the average of all these things, you can see July, August, and June, July, August, the insolation is quite low because of the rainy season. So this is the kind of, and this is available on NASA's website as well. You go to NASA's website, it will give you all the details. The tilting angle needs to be calculated, but basic data is given. So energy, before the energy assessment, before you calculate the size of the power plant, you also have to reduce the consumption of the energy. So instead of CFL, you can use LED lights, fan 3 or 5 star regulated, 3 5-star rated equipments. You can use, if there are a lot of water heaters in the house, then you could switch to solar water heating system instead of putting the solar water heaters. The water heaters on the on solar. Use environmental inverter ready fridge, soft starters. So all these things need to be considered. You have to conserve power and then design a power plant. Don't design the power plant at whatever is the static electrical loads. So again, same thing, daytime, nighttime loads and the energy consumption, list the DC and AC cables separately. So that's about it. That's what you have to consider. And then this is the table which I had shown in the earlier presentation as well. What is the consumption? So because I don't want to go too much into the details, because from here onwards, the detailed calculations will start, and which will take probably another 2 or 3 hours. So I think, Milind, I will stop here.
Okay, now, Milind, we are open to questions. So if there are any questions, please, you can ask. If there are any questions, or anybody has any questions, you can ask.
Probably what I can do is I could have another 2-hour session in complete detailed designing.
We will surely organize one more for that, so that it gives a complete overview of how to design a system. So any questions you can put in the chat box, and sir will then 100% answer your questions. So, any questions? Milind and Nilesh, please check your questions.
Sudesh sir, I will check. Sudesh sir, I will check in chat box as well as YouTube link.
Pardon, I didn't get you.
Sir, hello.
Yeah.
Sudesh sir, there is one question from Sankesh. How is pure silicon obtained from sand?
Oh, so that extraction needs to be done. I mean, usually sand has, I think Indian sand has around 1 or 2% silicon. So you have to extract that silicon out of sand, which means it's a furnace process.
Okay. And why silicon is mostly used for solar panels, not other semiconductor?
No. It is not that way. Commercially available solar cells are silicon, but there are amorphous silicons also. There are germanium-based semiconductors also. Amorphous. There is cadmium telluride, and there are amorphous and there are organic also. Silicon, why? Because there is nothing unknown in silicon. People have been studying silicon for quite a long time. It is commercially viable. It is not that there are no other semiconductor material which cannot be made into solar cells. It is not that way. It is commercially viable right now.
Okay. Means for commercial purpose we can use.
Yeah, it is for commercial purpose only. I mean, there are organic solar cells as well. They are not yet viable now. Efficiencies are that way quite low. But I'm sure they will.
What is that? Good afternoon, sir. Dinesh here.
Sir.
Milind sir, can I ask a question?
Yes, sure, sir.
Sir,
you can
just apprise us of what would be an initial investment to have this kind of a setup in, for example, a college like ours, sir. We have a huge area, and we initially have now only a few panels which run on batteries.
Okay.
But sir, what would be or can we do it phase wise, and we have a terrace as you spoke about, where we can find the inclination, we can have those inclinations, and you can rotate the panels as per the the sun. Yes, sir.
So I mean, I will make an assumption that the grid availability in Bandra is good. So there is no grid disconnect. So
yeah, that's true, sir. Yeah, that's true.
It's better to go with grid tied system, which means, I mean, roughly the market cost now is around 35 to 40 rupees a watt peak, which means around 35. So around 40,000 per kilowatt. So which means if you have a 10 kilowatt system, if you want to, what you will have to do is you will have to look at your bill. What is your connected load? And then from the connected load, you multiply that by, around 40,000 per kilowatt. You will get a number approximately. So for example, if your system loads are around 25 kilowatt, then it should roughly cost you around 10 lakh rupees. And the kind of energy saving which you make by going solar, I mean, you can have your return on investment probably in 3-4 years. Even if you consider 5 years, and if the solar power plant life is 25 years, you are consuming 20 years free energy. But right now, what is happening is that the power utilities are becoming smarter. They are not letting people install solar power plants on the roof. I mean, the rules and regulations are changing because the power utility is losing a lot of its business. Like for example, your college, if it converts into solar, then you will consume very less grid power, which means it will be a loss for the the power utility. But roughly it costs 40,000 to answer your question, 40,000 per kilowatt. So if it is a 10 kilowatt system, it will be 4 lakh. If it is a 25, it will be around 10 lakh or so.
Yeah. Sir, of late, sir, we have been receiving a lot of business models in our college, sir.
Yeah.
And the business models is that companies approach us and they said that we will actually sell this, or we will make a setup and sell the solar power to you at a price that is little higher than what I would normally get it, sir. So is that a viable model to look at from a college point of view?
So see, these are usually called as the OPEX model, which means the person will come, he will install the power plant on your roof, and he will sell the power to you. But now, if you, I'm assuming that you get power from Reliance. If now Reliance is selling the power at 10 rupees per unit, why would you buy solar energy from this particular contractor who's charging 11 rupees? I would buy it at slightly less. I mean, I would say, okay, we can come down and we will say charge her 7 rupees or 8 rupees. That will be my,
Yeah, that is what the model they have been proposing to us, sir. Around 6 to 7 rupees.
Yeah.
And for 20 years, sir. That is what is the, the business model that most companies who come to us are now proposing to us, sir.
Yeah, so that is a viable, see, because for example, 50 kilowatt system, if you want to install, just for argument purpose, you will spend 20 lakh rupees. Now, if I am doing, if I'm running a college, then if I have, say, 20 lakh rupees, I might buy computers, I might buy library books, I might increase furniture and infrastructure. I would not spend in solar, because as it is, that power which you're taking from the grid, you are breaking it in 12 installments. So instead of, and there are a lot many people who do that. If it is not their core business of energy, then they definitely go for the operation model. Someone will sell the power.
Okay, sir. Thank you so much, sir. Thank you so much, sir.
Yes, Sudesh sir, there is one more question from Naveen sir. He's from our physics department. With HIT technology, that is heterogeneous intrinsic thin layer technology, under research in Europe, it is said to be increased. We can increase or we can enhance efficiency to 28%. Is it true?
No. See, heterogeneous means a multi-layer. It is more than 28%. It is almost touching 40%. The last number, I mean, I could you share his email. I could probably send a slide which shows how the heterogeneous. It is more than 40%. That is possible because there you are trying to harness the whole solar spectrum. Right now with silicon, probably you are taking into consideration the green band. Multi-layer, you are actually harnessing the whole solar spectrum. Definitely the efficiencies are more.
Okay. Yes, thank you so much, Sudesh sir. Thank you so much.
Thank you.
Yes, any questions, dear student, from your side? Please ask.
Milind, there is a question, sir. In India, is silicon solar cell made, and is the solar cell harmful to ecosystem?
Not that I know of. Yeah, but then harmful in a sense. After 25 years, what do you do with that silicon cell? So in that way, again, it goes back to the sand. But then, in that environmental impact, people have not thought of environmental impact of 25 years. After 25 years, what happens? What happens to the batteries after 5-6 years? What do you do? That environmental issue is always there. It has to be tackled day in and day out.
Okay. Sir, there is one more question from student Famatai. Is there any other more efficient ways to store solar energy than electrochemical tubular batteries besides lithium-ion batteries?
Oh, there are many other ways. There is I don't remember exact name, but there is some liquid kind of thing. I don't remember. Yeah, but then there are many other ways. But everything comes down to cost, commercial
Okay.
viability. So right now the batteries are batteries in lithium ion, VRLA, whatever batteries you choose, they are commercially viable, and that is why they are more popular.
Okay. There is one more question from our participant, Stewart. Is it possible to get Perso white panels in Mumbai?
Possible to get
Uh, Persco white panels.
Swarovski. No. Again, I mean, they are available but not commercially.
Okay.
They are not commercially. So everything comes down to commerce.
Okay.
So the
Yes.
science and engineering both have to work together to get equipment to commercial viability. Probably 15, 20, 25
Okay.
years, 15 years back, silicon was not, because solar cells were not viable. But now they are viable. I will just give you a
Okay.
perspective. 2009, when I started construction of the solar power plant, it costed 12 crores per megawatt. And now in 2020, the same
Okay.
I can build for 3 crores. So you can see the costs have gone down drastically. It is scale of economy also, and commercial viability increases because scale increases.
Okay. There is one more question from Bharat. Can multiple panel at different places, and can we merge power in one place to
Yeah,
transfer
it is possible. It is possible.
entire power?
Yeah, it is possible. It is possible.
Okay. Yes. And sir, can we visit? Can you arrange one field visit
Unfortunately,
if
I will
possible?
do field visit,
If
but then
possible.
field visit in Mumbai, I have to look, because there are not many. I mean, I have not built any plant in Mumbai, but then in outside Nagpur, Chandrapur, all these places I have plants. And if anyone is interested in coming to Kabul, I can take them around.
Okay. Sure, sir.
I will try to look for a plant in Mumbai. I will let Dr. Kiran Jatar know about it. I will look into it.
Yes, then we can see exact what are the exact panels, control panels, different types of
I
electrical circuit required for a particular design.
I will.
Actually,
Yes,
Milind,
dear student, if you have any
I would have loved this session of offline, because
nice
interaction
presentation,
offlines
nice.
are really good, but due to this COVID situation, we are not in a position to do it offline. Even I think Dr. Sudesh would love to do it offline.
Yeah.
So
Unfortunately, I cannot see anyone. No, I can
yeah,
see myself.
yeah, that's true. So
Yes.
probably when the situation is better and we can do it offline, we can
Sure,
also go for a field visit. That would be really nice.
sure.
Yes,
Okay.
yes,
Yeah.
yes.
So
Namrata ma'am,
if there are no more questions,
I
uh,
think no, there is no question.
yeah, then I would request our HOD of Physics Department, Ms. Namrata Ajwani, to propose a formal vote of thanks.
Thank you, Kiran. At the onset, Sudesh sir, thanks a lot. It was a wonderful session.
Thank you.
Wonderful in the sense, right from the basics to the applications, to how does the concept, how is the concept to be developed, how the costing is to be done, everything has been covered. Yes, we would all have loved it offline. In fact, Dr. Kiran did ask me 2 days back, should we go for an offline session? But since getting 50 students and then having it in a big auditorium, still creates, like, the students keep talking. That's the reason why. And with COVID, I was a little skeptical on holding it offline. But sir, I know it would have been much better to have it offline. But anyways, we have had such a good session. I would like to thank our management, HSNCB, our principal, Mrs. Neha Jaktiani, who's been always supportive. I would like to thank DBT Star Scheme for helping us with funds for having such an event. Thank you, Dr. Mona. Thanks to Dr. Kiran Jatar for making this happen. The entire chemistry department, the physics department, and the students who have attended the event, made it successful. Thanks, other college staff also. I believe a lot of other college staff members were there for this session. Thanks a lot to all of you all, and we hope to have a field visit very soon. Very soon, and Dr. Bhagwat would really do wonders again, is what we all believe. Thanks a lot, sir. Thank you, and nice to listen to you. Thank you, sir. Thanks a lot to all.
Thank you.
I think we can leave the meeting.
Okay, thank you.
Thank you, sir.
Thank you.